Smart people love to think intelligence is a force field. It isn't. Nobel-level brains, billion-dollar machines, and the tiny, stupid mistakes that vaporized all of it. A screwdriver, a missing dash, one unchecked server. None of these people were dumb. That's exactly what makes it terrifying. Stick around. Let's start with the cruelest joke in this whole video. Karen Wetterhahn was a chemistry professor at Dartmouth who studied for a living how toxic metals poison the human body. This was her field. She knew more about heavy metal toxicity than almost anyone alive. So when she needed to handle dimethylmercury, one of the nastiest neurotoxins humans have ever cooked up, she did the responsible thing. She worked under a fume hood. She wore gloves. She followed the protocol that everyone in 1996 believed was safe. That's the part that should keep you up at night. She did everything right by the book. The book was just wrong. Here's the science. Dimethylmercury is a small, fat-loving molecule, and your standard disposable latex glove is basically a screen door to it. When a drop or two landed on her gloved hand, the poison didn't sit there politely. It soaked straight through the latex, through her skin, and into her blood in seconds. She felt nothing. No burning, no warning, no oops. For months, life went on completely normally. Then, about 5 months later, the bill came due. Her speech started slurring. She lost her balance, her coordination, her vision. By the time doctors tested her, the mercury in her blood was around 80 times the toxic threshold. 80. There was no treatment on Earth that could pull that much mercury back out of a human nervous system. She slipped into a coma and died less than a year after those 2 little drops touched her glove. And here's the gut punch. Her death rewrote the safety rules she'd spent her career building. Labs everywhere switched to laminated gloves, ditched dimethylmercury wherever they could, and started treating the stuff like the assassin it is. She protected thousands of future chemists by becoming the warning label. Now swap the gloves for a cheap plastic syringe. Sherry Sanji was 23, a sharp research assistant in an organic chemistry lab at UCLA. And she was working with a chemical called tert-butylithium. If you've never met it, here's the one fact you need. It's pyrophoric. That's the polite science word for bursts into flame the instant it touches air. Not might catch fire. Will. Every single time. No spark, no flame, no warning. Air is the trigger. There's a correct, boring way to move this stuff. A tightly sealed glass syringe, slow hands, full coverage, and you treat it like the angry liquid it is. What Sherry had was a plastic syringe whose plunger could slip straight out of the barrel. And she wasn't wearing a lab coat because nobody had drilled into her that she absolutely needed one. You can already see the freeze frame coming. As she drew the liquid up, the plunger popped out. The tert-butylithium hit the air and lit instantly, spraying burning chemical across her clothes and skin. There is no fire extinguisher that acts that fast. She suffered burns over roughly 40% of her body and died 18 days later. And this is where I stopped joking, because the failure here was not hers. California's safety regulators dug in and found the lab had no real safety training, no documentation, and wasn't enforcing basic protective gear. The professor running the lab, Patrick Heron, actually got hit with criminal charges. That is one of the only times in American history a scientist faced jail over a lab death. The case eventually settled, but it lit a fire of its own under university safety culture nationwide. The scientific lesson is brutal. In its simplicity, pyrophoric reagents don't forgive bad equipment. And "we've always done it this way" is not a safety protocol. A throwaway plastic syringe and a missing lab coat ended a 23-year-old's life inside an institution stuffed with geniuses. Drop a comment if a workplace ever handed you something genuinely dangerous and gave you a shrug instead of training. I've got a bad feeling this section is going to fill up fast. Time for the most famous screwdriver in physics. Los Alamos, 1946. Louis Slotin is a brilliant nuclear physicist, and he's running a demonstration that the other scientists nicknamed Tickling the Dragon's Tail. Read that again. They named the experiment after a thing that eats people, and then they kept doing it. Here's the setup. There's a plutonium core, later called the Demon Core because of course it was. Slotin is lowering a beryllium dome over it. Beryllium reflects neutrons back into the plutonium, and if you close the gap too far, those reflected neutrons kick the core into a runaway chain reaction. The official, approved method used solid metal shims to guarantee a safe gap. Slotin's method? He held the two halves apart with the blade of an ordinary flathead screwdriver, twisting it to control the gap by hand. Let me say that plainly. The only thing between a room full of people and a burst of lethal radiation was one guy's wrist and a hardware store screwdriver. You know how this ends. The screwdriver slipped. The dome dropped. The core went supercritical. The air flashed blue from ionization. The radiation alarm screamed, and Slotin yanked the dome off with his bare hand to kill the reaction, taking the full dose himself in the process. He almost certainly saved the other 7 people in the room. He died 9 days later as his body came apart from the inside. And here's the detail that makes it a genuine classic. This was the second time this exact core killed someone. Less than a year earlier, another physicist named Harry Daghlian had a criticality accident with the same lump of plutonium, and he died too. The thing was a 2-time killer before they finally retired it. The science is almost insultingly simple. In a criticality accident, geometry is everything. A few millimeters of gap is the line between harmless paperweight and death flash. Slotin understood that better than nearly anyone on the planet. He just trusted his hand more than he trusted the rule book. Comment time, and I mean it. Was Slotin a reckless cowboy, or a hero who cleaned up his own mistake in 2 seconds flat and paid for it with his life? I honestly cannot decide. Make your case below. Our next disaster was scheduled. Not the accident, the pressure that caused it. Soviet Union, 1960. They're building the R-16, a new intercontinental ballistic missile, and Marshal Mitrofan von Nedelin wants it tested before November 7th, the anniversary of the revolution. Because nothing screams sound engineering like slapping a political deadline onto a fully fueled nuclear-capable rocket. The rocket is on the pad, loaded with hypergolic propellants, fuel, and oxidizer that ignite the instant they touch each other. No spark needed, no ignition system, just contact. During final prep, they hit electrical problems. The textbook move, the only sane move, is to drain the rocket and fix it cold. Draining takes days. The anniversary does not move. So Nedelin did the unthinkable. He ordered repairs done with the rocket still fueled and live. And to keep morale high, he had dozens of engineers and technicians swarming around the base of the thing. He even pulled up a chair nearby to supervise in person. Then someone reset a switch. That command told the second stage engine to fire while it was still bolted on top of the full first stage. The exhaust ripped open the fuel tanks below it, and the entire rocket became a fireball you could see from miles away. The people closest to the pad simply ceased to exist. The official toll, buried for decades, was 78 dead, including Nedelin himself. They reportedly identified him from a melted metal and his keys. And then the Soviets covered it up. The story they fed the world was that Nedelin died in a plane crash. The truth didn't fully surface until 1989. The science here isn't really about the rocket. It's about human factors. Hypergolic fuels are unforgiving on purpose. That's exactly what makes them reliable in space and lethal on a crowded pad. The fatal error was treating a live missile like a school project that could be rushed to hit a date on a calendar. Schedule pressure has murdered more brilliant programs than bad math ever has. Next up, a cooking show. Sort of. Japan, 1999, a nuclear fuel plant in Tokaimura. The job? Mix uranium into a solution. There's an entire automated, precisely controlled system designed to do this safely, specifically so you never pile up too much enriched uranium in one place at one time. Why does that matter? Because if you gather enough fissile material in the right shape, it doesn't need a reactor, a bomb, or a trigger. It goes critical on its own. Physics does not care that you're behind schedule. The workers were behind schedule. To save time, management had quietly written an illegal shortcut manual telling them to skip the slow automated process and just mixed the uranium by hand. So 3 technicians stood there pouring enriched uranium into stainless steel buckets and dumping it into a settling tank. A tank that was never designed to hold that much fissile material. Bucket 1. Fine. Bucket 2. Fine. They kept pouring. And when they tipped in the 7th bucket, the tank hit critical mass. There was a flash of blue light. That ionization glow again, the universe's way of telling you that you've made a catastrophic mistake, and the open tank became an open-air nuclear reactor. It stayed critical, on and off, for about 20 hours while crews scrambled to shut it down. The 2 men closest to the tank absorbed staggering radiation doses. One of them, Hisashio Uchi, took a dose so far past survivable that his case is now studied in medical textbooks. He was kept alive for weeks in a condition I will not describe in detail, out of basic decency. Both of those technicians died. The science is the scariest part. Criticality is purely about geometry, mass, and concentration. There's no explosion, no mushroom cloud, just enough of the right material in the wrong shape, in the wrong container, generating a lethal flood of radiation in total silence. The men with the buckets weren't told any of that. They were told to go faster. Here's one that turns entirely on a single dropped object. Arkansas, 1980. An Air Force crew is doing routine maintenance on a Titan II missile sitting in its underground silo. And bolted on top of that missile is a 9-megaton thermonuclear warhead, the most powerful weapon the United States ever fielded. Just a casual evening at the office. One airman is up on a work platform high above the missile. The rules now require a torque wrench for this job. He's using an old-school ratchet wrench instead, because it's what he's always used, and it's faster. A heavy socket, about 8 pounds of solid steel, pops off the end of that wrench and falls. It drops roughly 80 feet down the silo, bounces off a thrust mount, and punches a hole clean through the skin of the missile's first-stage fuel tank. Now there's a leak, and the fuel inside is hypergolic. Same nasty family as the Soviet rocket we just covered, which means the second it finds the oxidizer, it lights with no spark required. The silo starts filling with explosive vapor. For hours, crews fight to save it. They can't. In the early morning, the fuel finds its oxidizer, and the silo detonates. The blast launches the 740-ton silo door clean off and hurls the second stage and the warhead up out of the ground. 1 airman is killed, 21 others are injured, and the nuclear warhead ends up sitting in a ditch about 100 feet from the entry gate. Now, the genuinely reassuring part, and I mean this sincerely, the warhead's safety engineering worked flawlessly. It did not detonate, and it did not leak radioactive material. The bomb behaved far better than the wrench did. Whoever designed those warhead safeties deserves a statue. The lesson is almost stupidly small. A guy grabbed the wrong tool, dropped a socket, and nearly blew a nuclear hole in Arkansas. The whole event is a monument to one idea, that in high-stakes systems, the tiniest deviation can cascade straight into the unthinkable. What's the worst thing you've ever broken using the wrong tool? Mine's a phone screen and a butter knife. His was an intercontinental ballistic missile. Let's give your heart rate a break, because nobody dies in this one. Just $37,001,962 of NASA hardware, erased by a single missing punctuation mark. July 1962, NASA launches Mariner 1, America's first attempt to send a probe to Venus. The rocket lifts off, and almost immediately it starts wobbling, swerving, and generally behaving like it's had a few drinks before work. Range safety has to hit the self-destruct button less than 5 minutes in, blowing the rocket up over the Atlantic before it can crash somewhere it shouldn't. So what happened? Buried in the guidance software was a tiny transcription error. The accurate version of the story is that someone left out an overbar, a little line that's supposed to sit on top of a symbol in the equations, telling the system to use a smoothed, averaged value for the rocket's velocity. Without that bar, the computer stopped smoothing the data and started reacting to every tiny, meaningless jitter in the signal, as if it were a real course deviation. So it corrected, constantly, violently. It chased ghosts until the rocket tore itself off course. One missing line over one letter. The science fiction legend Arthur C. Clarke reportedly called it the most expensive hyphen in history, which is technically the wrong symbol, but the man wrote 2001, so we'll let it slide. Here's the scientific gold buried under the joke. This is the moment the world learned, the hard way, that software is infrastructure. A single character in a control system isn't a typo. It's a load-bearing beam. Modern code review, redundancy checks, formal verification, a lot of that discipline traces part of its DNA back to embarrassing craters exactly like this one. NASA learned, fixed it, and Mariner 2 reached Venus just a few weeks later. So while nobody got hurt, somebody, somewhere, sat through the single worst code review of their entire life. From a missing mark to a missing brain. This one comes with a villain you'll actually enjoy hating. Italy. 2012. The Costa Concordia is a cruise ship the length of 3 football fields, carrying over 4,000 people worth somewhere around $570 million. Captain Francesco Schettino is in command, and he decides he wants to do a sail by salute. That basically means steering this floating apartment complex super close to the island of Giglio to show off for people standing on the shore. So he takes a massive cruise ship off its safe, computer-planned route into shallow water at night near rocks to impress strangers he will never meet. What could possibly go wrong with parallel parking a skyscraper next to an island in the dark? The ship hit a rock. The rock opened a 160-foot gash in the hull below the waterline, and the sea came pouring in. The Concordia began to lift, lost power, and rolled onto her side in shallow water like a beached whale. 32 people died. And then Schettino delivered the part that made him internationally famous. While the evacuation was still a chaotic mess, he somehow ended up off the ship and into a lifeboat, well before his passengers were safely off. An Italian Coast Guard officer got him on the phone and, in a recording that became legendary, basically screamed at him to get back on board his ship. Schettino, with great commitment, did not. He later claimed he fell into the lifeboat. Sure, we've all accidentally tripped and landed in the one vehicle leaving the danger. The maritime principle here is ancient and crystal clear. In a disaster, the captain's first job is the ship and everyone on it. Full stop. Schettino was convicted of manslaughter and abandoning ship and went to prison. The salvage operation to haul the wreck off that island became one of the most expensive in maritime history. Now back to the Cold War and a submarine that earned a nickname no machine ever once. Soviet Union, 1961. The K-19 is one of the USSR's first nuclear ballistic missile submarines, rushed into service fast. And rushed is the word that's about to do a lot of damage here. Out in the North Atlantic, the pressure in one of the reactor's cooling systems suddenly drops to 0. A pipe has failed. With no coolant flowing, the reactor core starts heating toward meltdown even after the control rods drop in, because radioactive decay keeps generating heat whether anyone likes it or not. The core temperature begins climbing toward 1,400 degrees. Here's the design crime. The submarine had no backup cooling system installed. None. The blueprints called for one. The actual boat that went to sea did not have it. So the crew was staring down a reactor meltdown with literally no built-in way to stop it. What the engineering team did next is the exact opposite of stupid. It's pure, desperate courage. With no backup to fall back on, they improvised one on the spot, cutting into a pipe and welding together a makeshift cooling line by hand, working right next to an overheating, radiation-spewing reactor. They went in teams, only a few minutes each, because the radiation was beyond lethal. Their jury-rigged system worked. It saved the boat and stopped the meltdown. It also killed them. Several crew members died within weeks from acute radiation sickness, and many more died in the years that followed. The crew started calling the boat Hiroshima. The lesson here sits one level above the reactor. A safety system that exists on paper, but not in the steel, is worse than no plan at all, because it lets everyone believe they're covered when they're standing on nothing. The men who fixed it weren't reckless. They were brave people sent to see inside a machine somebody else cut corners on. Let's talk about losing $440 million in less time than it takes to watch a movie. No explosions, no radiation, just one server that didn't get the memo. Wall Street, 2012. Knight Capital is one of the biggest stock trading firms in America, the kind of company that handles a giant slice of all the trades flying around the market every day. Their entire business runs on automated software, making split-second decisions with real money. They're rolling out a software update across their 8 trading servers. A technician deploys the new code to 7 of them. The 8th? Missed. Skipped. Left running the old setup. 7 out of 8. So close to fine. Now here's the landmine. That update reused an old flag, a little on-off switch buried in the code. And on the forgotten 8th server, that flag accidentally woke up a piece of ancient, retired software from 2003 called PowerPeg. This old code was never supposed to run again, ever. It woke up cranky and started firing off stock orders like a slot machine that only knows how to lose. When the market opened, that one zombie server went berserk. In about 45 minutes, it blasted out millions of unintended trades and bought roughly $7 billion of stock the company never wanted. Every second it ran, it hemorrhaged money. The team frantically tried to figure out what was even happening, while the losses ticked up like a doomsday clock with a $sign on it. By the time they finally killed it, Knight had lost about $440 million. The stock cratered, the company nearly died overnight, and it had to be rescued and then swallowed whole by a competitor. One unupdated server ended a firm that took decades to build. The computer science moral is one every engineer gets tattooed on their soul after hearing this. Your deployment is only as safe as your least updated machine, and dead code is never as dead as you think. Reusing that old flag was the digital version of leaving a loaded mousetrap in a junk drawer for 9 years and then reaching in blind. This next one I'm going to handle gently because the person who got hurt did absolutely nothing reckless. Yale University, 2011. Michelle Dufault is a senior, a physics and astronomy major, brilliant, just weeks away from graduating. She's the kind of student who builds her own experiments from scratch, which is exactly why she's in the campus machine shop late at night working on a lathe for her senior project. A lathe spins a piece of material at high speed, so you can cut and shape it. It's one of the oldest, most useful machines in all of engineering, and one of the most unforgiving because it does not know the difference between a steel rod and you. The machine she was using dated back to 1962. It had no emergency shutoff switch within reach and no proper guard to keep loose material away from the spinning parts. While she was working, her hair got caught in the rotating spindle. With no guard to stop it and no emergency stop she could hit in time, the machine pulled her in. She died of accidental asphyxiation. Other students found her later that night. I'm not going to make a joke here because there isn't one to make. What there is a failure of the people and systems around her. She was working alone, late, which violates one of the most basic shop safety rules there is. The machine was a half-century old, missing safety features that any modern lathe ships with as standard. Tie your hair back, never work alone on rotating machinery, and keep an emergency stop within arm's reach. These aren't friendly suggestions. They are written word for word in stories exactly like this one. Her death forced Yale and a lot of other universities to overhaul machine shop safety. Mandatory training, buddy rules, guards, accessible kill switches. The scientific reality is blunt. Rotating machinery doesn't get angry and it doesn't get tired. It just converts whatever it grabs at the same steady speed, which is precisely why the guards and the stops exist. A talented young scientist should have walked across that graduation stage. Instead, she became the reason the next generation of students is safer. Let's talk about the most powerful magnet most people will ever stand next to, and the one rule that exists to keep it from killing you. An MRI machine is basically a superconducting electromagnet so strong it can rip a steel oxygen tank across a room like a fridge magnet grabbing a paperclip. That's not a dramatization, that's a documented failure mode. So the number one rule of an MRI suite, the rule, is dead simple. No metal goes in that room. Ever. Not a wheelchair, not a hairpin, not the wrong wedding ring. New York, 2025. A man named Keith McAllister goes in to help his wife, who's having a scan. He's wearing a large, heavy metal chain around his neck, the kind used for weight training. And here's the failure, and it is not his failure. The staff let him into the scan room while he was still wearing it. Reportedly, they'd even seen him in that same chain on previous visits. The entire job of MRI screening is to stop exactly this, and it didn't. The instant he got close enough, the magnet did what magnets do. It grabbed the chain and yanked him into the machine with violent force, pinning him against it. He went into cardiac arrest and died the next day. This is a bystander killed by a broken safety process, so I'm aiming every bit of my contempt at the protocol failure, not at the man. The screening checklist for an MRI room is one of the most idiot-proof procedures in all of medicine, precisely because the magnet never ever switches off. Here's the part most people don't know. It is always on, even when nobody's being scanned, even overnight, even when the machine looks completely dead. People assume it powers down between patients. It does not. That single assumption is exactly what kills. Back to space, and back to software eating a fortune, but this time with a twist that'll make every programmer in the audience physically wince. Europe, 1996. The European Space Agency launches the Ariane 5, a brand new heavy-lift rocket that took about a decade and $7 billion to develop. On board, roughly $500 million in satellites. 37 seconds after liftoff, the rocket tears itself apart and self-destructs. The cause is one of the most studied bugs in computing history. The Ariane 5's guidance computer was running a chunk of code recycled straight from the older, slower Ariane 4. It had worked perfectly on the 4. But the Ariane 5 was faster and far more powerful. So, one particular value related to the rocket's sideways velocity got much, much bigger than the old code ever expected to see. Here's the technical heart of it. That big number was stored as a 64-bit decimal value, and the code tried to cram it into a 16-bit slot that can only hold whole numbers up to about 32,000. The real number was way past that. This is called an integer overflow. Picture pouring a full gallon of water into a shot glass and acting surprised by the mess. The system threw an error, the guidance computer choked on it and shut down, and the backup computer running the exact same code choked on the exact same number and died too. Both brains gone. The rocket lost all sense of direction and ripped apart under aerodynamic stress. And the most painful detail? Engineers had only protected 4 out of 7 critical variables against this kind of overflow, partly to keep the computer's workload light. The one variable that blew up was one of the 3 they left unguarded. They shaved a corner to save processing power, and it cost $500 million in under a minute. The lesson is now basically a programming commandment. Reused code is not free, and it is not already tested. It is only tested for the world it was originally written for. Drop it into a new environment, and your old assumptions quietly turn into live grenades with the pins already pulled. This one is so dumb it loops all the way back around to being beautiful. Russia, 2013. A Proton M rocket is on the pad, carrying 3 navigation satellites. It lifts off, and within seconds, it's visibly drunk, veering, twisting, fighting against itself. A few seconds later, it noses over, slams back down toward the ground, and explodes in a fireball right next to the launch site. The investigation found the cause, and it is a genuine work of art. Inside the rocket are angular velocity sensors. Basically, the rocket's inner ear, the parts that tell it which way is up so it can steer straight. Some of these sensors have to be installed pointing one specific direction. They literally have arrows printed on them. The arrows are supposed to point toward the nose of the rocket, toward the sky. Someone installed 3 of them upside down. And here's the detail that elevates this from oops to how is this even possible. Installing them upside down was actually harder than installing them correctly. The parts had alignment pins designed so they'd only fit the right way. To force them in backwards, someone had to ignore the pins, shove past the resistance, and physically damage the mounting plate doing it. Investigators literally found the scratch marks. A human being had to fight this rocket to make it this broken. So at liftoff, the rocket's inner ear was confidently reporting that up was down. The flight computer, doing its job perfectly, saw that it was falling and frantically steered to correct, driving the rocket straight into the ground it was trying to climb away from. The hardware worked. The software worked. The human installed reality itself upside down. The engineering principle here is one industrial designers obsess over. It's called poka-yoke, mistake-proofing designing parts so they physically cannot be installed wrong. The Proton had it. The alignment pins were right there, doing their job. And one determined human defeated the mistake-proofing through sheer brute force and overtime. What's something you've assembled where you forced apart in the wrong way because it almost fit? IKEA confessions, absolutely welcome. Yours probably didn't explode on a launch pad. Probably. Now let's go big. Specifically, the biggest non-nuclear explosion human beings have ever accidentally made. Soviet Union, 1969. The space race is on, the Americans are about to land on the moon, and the USSR's answer is the N-1, a giant moon rocket taller than a 30-story building. To get that monster off the ground, Soviet engineers strapped 30 separate engines to the bottom of the first stage. 30. Coordinating 30 rocket engines firing in perfect harmony is an absolute nightmare of plumbing, timing, and vibration. On the second test launch, the rocket lifts off the pad, and almost immediately, things go wrong down in that forest of engines. A turbo pump in one of them fails. Debris scatters. A fire breaks out. The engines shut down. And the rocket, now barely off the ground, leans over and falls straight back onto its own launch pad. Fully fueled. What happened next? Released roughly 7 kilotons of energy. For scale, that's a meaningful fraction of the Hiroshima bomb, except entirely chemical. No atoms split. It's widely cited as the largest artificial non-nuclear explosion in history. The blast flattened the launch complex, blew out windows miles away, and threw debris as far as 6 miles from the center. The pad itself was out of commission for a year and a half. The one genuinely good decision in the entire story. The pad had been cleared of people for the launch, so nobody was killed. After the Netherlands disaster 9 years earlier, that's a lesson the Soviets had bought at a horrific price, and this time, actually kept. The engineering takeaway is all about complexity. Every engine you bolt on is one more thing that can fail, and the N-1's 30-engine design multiplied the odds of exactly this kind of cascade. The Soviets never did tame it. The N-1 failed all 4 times it ever flew, and the program was quietly canceled and erased from the official story. Sometimes the simplest path to total failure is just building something too complicated for anyone to control. Comment question for the engineers. Is it better to build one giant engine or 30 small ones? The Soviets bet everything on 30 and lost. Last one, and it's a slow-motion fender bender, except in orbit at thousands of miles an hour. 1997. The Russian space station Mir is aging, cramped, and held together with duct tape and pure stubbornness. The cosmonauts are running a test of a manual docking system called Toru. Instead of letting the automatic system guide an incoming Progress cargo ship to the station, a cosmonaut flies it in by hand. With a joystick, watching a video feed. Cosmonaut Vasily Sibliev is at the controls, trying to manually steer a 7-ton unmanned cargo ship toward the station. Now stack up the problems, because they stack high. Mir had no docking simulator on board, so he hadn't practiced this maneuver recently. The Progress was heavier than expected, thanks to a ground loading error, which changed how it responded to his commands. And on top of all that, the setup left him without a clear, reliable view of the incoming ship's speed and distance, until it was basically too late to matter. By the time the cargo ship came into clear view, it was moving too fast and he couldn't kill the speed in time. The Progress plowed into Mir, clipped a solar array, and punched a hole straight into the Spectre science module. The station's air began rushing out into space, The first depressurization ever to happen aboard a crewed spacecraft in orbit. The crew scrambled, cut the cables and hoses running into the leaking module, and sealed it off, deliberately sacrificing Spectre and a big chunk of their science experiments to save the station and themselves. They survived. Mir limped on, but they permanently lost an entire module. So what's the thread tying all of this together? Every single person in this video was smart. Not pretty clever, genuinely brilliant. Nobel-adjacent physicists, elite engineers, ship captains with decades at the helm, programmers trusted with billions of dollars. Intelligence saved exactly none of them. A screwdriver, a missing line of code, an upside-down sensor, one skipped server, one chain in the wrong room. The mistakes were almost insultingly small, and the results were anything but. Maybe that's the real lesson. The great disasters of history usually aren't caused by stupid people doing stupid things. They're caused by brilliant people who got comfortable, skipped one step, and trusted themselves over the rulebook. And the rulebook, it turns out, was written in other people's blood. If you made it all the way here, you're my kind of person. So do me a favor, hit subscribe because we are absolutely not done collecting these. Then settle the argument in the comments. Out of every case tonight, which one was the most avoidable? Which genius should have known better? Make your case, defend it, and feel free to fight about it down there. I'll be reading every single one.